So my name is Mark Kittisopikul. I'm a software engineer at the Geneva Research Campus of HHMI. Um, we are basically a biomedical research campus that kind of tries to takes on larger projects. Among other things, like our previous speaker, we are in the business of kind of building microscopes, so that most of what we do build are prototypes. As such, we do have a big interest in open file formats. So today I'm going to be talking about using HF5 as a Zarr v3 shard. So I'm trying to cross-file format here, and I'll explain why. Basically, from my perspective, we have a bit of a problem because we have multiple competing formats. Standards are proliferating, as this cartoon kind of makes fun of a little bit. And for me, if I can figure out how to basically output one thing and have it be compatible with multiple formats or APIs, this makes my life easier. Um, and namely, we are largely a data manufacturing facility. We produce a lot of data, terabyte to petabyte imaging data sets. And we can't really afford to make duplicate copies of these just to satisfy one format or the other. And ultimately, kind of what my objective here is to make it easier for our downstream users, our image analysts, or processors, which very well might be me actually at the end of the day. Want to make it easier for people to read these APIs and load them into the various algorithms that are out there rather than having to reinvent these or re-interface these. Okay, so what is RV3? Gerd alluded to some of these in his talk. These are one of these so-called cloud optimized formats. Um, Similar to kind of what the previous speaker addressed, it's a combination of having a JSON file, in this case, which version 3 called star.json, which contains both the file and format metadata as well as user metadata. One of the distinctive features of Zarr is that chunks, it's very similar to chunks in the HDF5 dataset, but in this case, chunks are stored as individual files. And if you ever used chunk data sets in the past, you may know that this quickly could proliferate. We would end up with millions of files, which can be a very annoying problem. And I think our previous speaker also mentioned that having just a few files can be problematic on an instrument, and this makes it very problematic to use because it's harder to move this data around. So something that has kind of come around here is, well, they said, well, what happens if we took multiple chunks and put them into one file or one key in an object store, such as Amazon S3? And they would call these shards. And technically, the way that this has been implemented is as a codec. That is that each of these shards are technically chunks, and they've been subdivided into smaller chunks. Taking a look at this is very reminiscent of HDF5. And so one question that I immediately asked as I saw this being developed, started interfacing with this, is could an HDF5 file also serve as a star shard? It's a slightly different perspective, but conceptually the idea is the same. We have a file and we have chunks that can be individually compressed within that file. The star 3 shard specification tries to be as simple as it can be. Basically, the metadata to locate chunks is very simple to find. It's either at the beginning of the file or it's at the end of the file. Um, it's hard-coded to be 64 bits for both offsets and sizes of the chunks, and it ends with a checksum. In this case, CRC32C. And kind of the idea and inspiration behind this is that this chunk index can be easily retrievable from the cloud via single HTTP GET requests using a byte range header. So basically, you could say, I just want the first n bytes of the file. If you've already parsed that JSON file, you know exactly how much to ask for. And so, and looking at this and reading the HDF5 specification, I realized this is very similar to what's called a fixed array data block in version 3 of the HDF5 specification. Basically, in an HDF5 file, there is a format to kind of encode the address or chunk size, as well as this filter mask for each chunk. And this begins to look very similar to what I just described in terms of star v3 shards. As you can see, the address is variable size, but we could make it 64 bits. There's also this filter mask, and that's because in HDF5, chunks filters can be optionally applied. And so with this filter mask, basically this is just a bit field, and I believe this is usually always 32 bits because you can have up to 32 filters. And so we can also basically suggest that the chunk size could be 32 bits by indicating this, I think, in the fixed array data header. Comparing it to Zarr, I think this actually starts to line up pretty well. And so, I think the thought to cross my mind whether we could reuse a fixed array data block as a Zarr v3 shard index if we were able to just locate this data structure at either the beginning or end of the file. It turns out at the end is a little bit easier. There is one hiccup though, which is that we use Bob Jenkins lookup 3 checksum and HDF5, whereas Zarr is using CRC32C. So unless we have the option HDF5 to use CRC32C, which I think is something we should consider in HDF5 too, especially since there's now tremendous hardware support for CRC32C. That said, the other way would be also teaching Zarr about Jenkins lookup 3. Okay, so basically the idea here is we're going to start with a cloud optimized HDF5 file that Gerd alluded to. And there's several ways we could combine the Zarr v3 shard specification with HDF5. One would be to embed the Zarr v3 shard in the HDF5 user block. Then this would be followed by HDF5 metadata at some specified offset. And basically, both Zarr and HDF5 would be pointing to the same shared data chunks. Another option would be we again use cloud optimized format, consolidate all the HDF5 file metadata up front, and we position it so that we have a second contiguous data set that acts as a Zarr v3 shard at the very end of the file. This is a little bit more treacherous, but on the other hand, you can address this extra Zarr v3 shard index directly via HDF5. And the last option, option C, would be to perhaps consider a shared data structure, although we would have to deal with the checksum problem. So the sharding concept, though, is conceptually similar to an existing HDF5 feature, which is a virtual data set. Essentially taking this figure 1 from the virtual data set RFC, we could basically see that we've taken a single array HDF5 data set and broken it up into 4 parts. And this is exactly what the Zarr folks are doing. They're just doing it in a less flexible manner. It has to be evenly partitioned up front in a particular manner. But basically, each of the source data sets live in particular files or keys that are basically prescribed instead of having to individually map all these. And so I think this is another thing that potentially HDF5 could adopt would be some kind of fixed naming scheme for source data sets for regularly divided virtual data sets. And so the idea here would be if we wanted to have a data set that is both an HDF5 virtual data set and a combined Zarr array, we basically could use this scheme. We could use Zarr's existing naming scheme, which is as a version 3 starts with a C and basically breaks up the components as follows with 0s and 1s, as I've shown here. And essentially, we would just create an index HDF5 file, which contains a virtual data set pointing to these 4 components, which are individual HDF5 files containing a single data set, or maybe 2 data sets, with one of those being a Zarr v3 shard. Meanwhile, Zarr would have a JSON file. This would also contain the sufficient metadata for the Zarr specification to locate these files and also read those same chunks. Okay, so let's see. I might be a little bit fast. You can tell me a little bit. So I have a bonus topic we can go into. But basically, the summary here is that SRV3 shards partition chunks into smaller inner chunks. We can think of this basically as this HF5 virtual data set um, extension, but basically as something that's a little bit more rigid. They have to be identical partitions. Um, and basically, I've laid out a number of ways in which we could make a single file or, in an object in a key value store to be both HF5 file and a SRV shard. We could either use a user block, we could use an extra contiguous data set at the end of the HF5 file, or we could start thinking about how we could align checksums in order to maybe reuse existing HF5 data structures as a SRV3 shard index. I think there's alternative approaches. I believe there might be um, one, I think, later this week, where I believe someone is using NetCDF to read star files. So there's an API-based approach. We could also consider some kind of virtual file driver for HF5 instead of using these kind of formatting approaches. Since I think we do have extra time, and feel free to correct me if I'm wrong, I'm going to go into a slightly bonus topic where I've demonstrated this for another crowd, that is particularly a microscopy crowd, looking into how we would save formats from a microscope, as the previous speaker kind of went into. And so I'm going to add a third dimension to this, which is combining TIFF file format with this. TIFFs are very common in my field, and but they do have the problem that they are usually planar in terms of how they save files. However, there have been extensions in the geosciences community which allow for tiles and then actually extending those tiles into true 3D chunks. TIFF metadata can be cloud optimized as well, so we can consolidate all the TIFF metadata right at the front of the file. As we've mentioned, HF5 has a user block feature, which allows for space at the beginning of the file and HF5 metadata to be consolidated just after that. And the SRV3 shard specification allows for file-based metadata to come at the end of the file. And so the idea here is that we basically could combine all these features into a single file that's simultaneously a TIFF file, simultaneously an HO5 file, and simultaneously a SAR file with image chunks somewhere in the middle of this sandwich. Basically, since we've been in prototyping and building microscopes, we need something that was very easy for my microscope builders to implement. Essentially, what I've done is we've created a template-based system where we have kind of these 2 GB binary templates. I give them an offset to fill in the data with. They capture frames from their cameras, do a dimension permutation to chunk this data, and basically combine this into a single file where we have basically a file that can be read anywhere, any way that my users would like, either as a TIFF file, as an HO5 file, or as a SAR file. And I basically do have a quick demonstration here in Jupyter Notebook form. This is maybe started as a slightly different project than I ended up with, but I was trying to basically cloud optimize and simplify these data formats so I could figure out how to combine them. And so maybe it's not so simple image formats. But basically what I'm demonstrating here is first I'm using H5Py to create the template for this. And basically I'm showing that once I have one of these files, we can use H5Py, libtiff, or TensorStore, or SAR, or API and library, and we can read the exact same data, which is chunked, using all 3 of these APIs. Furthermore, we can use H5Py to go in and modify the data, and then we can again use all 3 of those APIs to read back the modified data. And so, in summary, basically, I've created a combined file format by basically studying each of those file formats using a cloud optimized format to consolidate the metadata. And once I have consolidated metadata, it becomes very easy to combine multiple formats together because they just fit together like Legos. Um, these are just a few implementation notes, and I think that will be the end of my talk. So thank you. Any questions?
Thank you. Questions? Oh, Elena, go ahead.
Sorry, I don't want, maybe someone else has questions. No?
No, go ahead.
Okay.
Go ahead.
Mark, have you considered using wall connectors for HDF5? Then you do not need to combine any formats, but really create wall connectors that can be dynamically loaded, and it will be transparent to H5Py.
Yeah, I think that's kind of what I was alluding to with a virtual file driver, or a wall connector would also kind of do something very similar. I think in talking with Dana, I think this is something we've basically laid out that should be possible, right? In some ways, SARS only implementing a subset of the HFI specification in a way, and there should be a way to do a mapping of that. And yeah, I think that would be quite possible. And that would avoid some duplication. Um, that said, the amount of duplication that I'm talking about is really in the kilobyte range. And, um, for dealing with things in the terabyte to petabyte range, that's acceptable for me at the moment. And so, but yeah, that's something that I think we should consider going forward.
All right.
Thank you, because Ed and I were talking that it would be good to have wall connectors, and then NetCDF can read whatever. They have a lot of access to different formats. But if HDF5 has wall connectors, it also will simplify for every library that sits on top of HDF5.
Absolutely.
I think there was one question in the chat. Is that what I saw? From Alex. Do you see the chat? So he says,
See the chat. Let's see. Oh, that's just saying I thought Zarr was only compatible with Python. That was one of my drivers for exploring HL5. And have you looked at the next generation of file format that open microscopy environment is building? Yes, I have. I just came from an open microscopy environment user group meeting where we were discussing NGFF. At the moment, the so-called next generation file format is basically a microscopy format for life sciences. And the current specification is entirely based on Zarr, although I think some of us have advocated for this to be maybe container neutral and trying to see if we can come up with an HDF5-based version of that format. Zarr, one thing that the Zarr community has encouraged is actually a lot of multiple implementations. And so we have Zarr implementations in Rust, Java, JavaScript, and Google has a library called TensorStor, which I mentioned, which is implemented in C++. So it very much is accessible from many different languages at the moment. And I think that I think we've recently seen a Java implementation of HTML5, and to some degree, I think it would be great to also allow people to create their own libraries and help them with that. And so that's something I would like to see it from a community perspective as well.
Okay. Any other questions online or in the room? Oh, one more question here.
Hi, thanks. It would be like our community would be very benefiting from having access to these free file formats, yeah, effectively without additional storage and conversions needed. I was curious because I'm not so familiar with Zarr. What about these shards? Can I have compressed data there? And will that also work with HDF5 then?
Yes. And so in many cases, the codecs for Zarr are similar to those in HDF5. So things like C standard would work, and and yes, in terms of like for read-only data sets, that would absolutely work. It does get a bit complicated when you're kind of writing, because the size of the individual chunks may change, and so if you have two separate indices, you may have to update one or the other, or you have to update both indices in order to keep the data integrity consistent. Um, but yes, that's something that I think maybe initially inspired Zarr, because having each chunk in individual files or individual keys allows for massive parallelism across that. Although I think we've heard of alternative strategies from Francesca this morning, and maybe you'll hear about some more later on.
Okay, thanks.
Any other questions? All right, let's thank our speaker again.
Yeah, thank you.